Yes?
Done.
Okay. Housekeeping announcements to begin. First, there's the first homework that we'll hand back at some point, so come up after class if you haven't got your first homework, and you can get it back. It's sort of graded on a scale, check plus, check minus. So a fairly simple scale, but we've read through things. David's read through things. Verified everything. This week's, or last week's homework, I guess, please put it on the file before you leave today. And there will be another homework up later today. It's due Friday, which is not very much time for the compressed nature of IAP, so it'll be a shorter homework, and it will cover things basically up to this lecture. But from now on, we're sort of, the course, if anything picks up in pace, I'm going to show you more things, and there's plenty of time to talk about it if you want to talk about them, but it won't be on the homeworks. Okay. Okay, so last time we saw these things called signal flow graphs, which I used in engineering to talk about the way sort of signals or differential equations sort of flow between different parts of a system. And we also saw this notion of a prop, which was a certain simple form of symmetric monodal category. So I'm going to continue the story, and in particular bring in notions about linear algebra, which helps understand why signal flow graphs are so useful in engineering. But let's begin on a more category theoretic note. We talk about free structures, in particular free props. So we've said the word free occasionally throughout this course, and we've given a way of generating a whole lot of structures. So we said that if you want a poset, one way to get your hands on a poset is to present it using a Hasse diagram. So, and it turns out you can present every poset in this way, or pre-order in this way, but there's this idea that the directed graph presents the pre-order, and there are many different ways to present a single pre-order. So, for example, you could just have, here's a pre-order with one element, a presentation of it, but here's another one. And in both cases, there's sort of two different directed graphs that you can generate a pre-order out of, but for the same pre-order. So what I want to do is link this notion of freeness or presenting things, whether they be pre-orders or categories. We've also seen how to present them as using directed graphs, with the notion of a junction, to give you some idea about how junctions are used and also how to understand abstractly what freeness means. But I'll just give you two examples in this vein. So the first fact I want to tell you is that the natural numbers as a monoid, so with plus and 0, is the free monoid on a set, on a set with one element. So I'm just going to call that element 1. So one way to understand this, or one property of the natural numbers, is that if you look for functions, so you could consider the set of functions, this Hom set of morphisms from 1 to any other set. Let's say it's the underlying set of a monoid, so I'm going to write Un. So this is the set of functions from 1 to underlying set to underlying set of a monoid. So it's possible to observe that these things, these functions, one-to-one correspondence with monoid homomorphisms from the natural numbers to M. This is monoid homs. Right. So how do we go between these? Well, let's start here. If I have a monoid homomorphism from the natural numbers to some monoid M, then I can think about where the element 1 goes. And that's a function, and where that goes describes a function from the element 1, or the set containing the element 1, to the underlying set of the monoid. More interestingly, we can go the other way. If you have a function from 1 to the underlying set of a monoid, you can extend that to a monoid homomorphism from the natural numbers to M in a unique way. So this is a one-to-one correspondence. What is that unique way? Well, if we know where 1 goes, we need to think about where does 0 go? It goes to the unit of the monoid, because it's a monoid homomorphism, so it has to go there. And where does, say, 2 go? Well, 2 has to go to 1 plus 1, right? So if, note, if we call this thing the monoid homomorphism F, then F of 2 is equal to F of 1 plus 1, because 1 plus 1 equals 2, which has to go to, I call this times for the monoid operation, right? So F of 1 plus 1, by the homomorphism property, needs to go to the product of F of 1 and F of 1. So we know where 2 goes. And similarly, we know where every natural number should go. N goes to the product of n copies of F of 1, which is just the image of 1. So more abstractly, we can think about the category of sets, the category of monoids, and we have a free functor that sends a set to some sort of free notion of monoid on that set. So here it's this functor set 1 to the natural numbers. We have a functor back the other way that takes a monoid and tells you its underlying set. And there's this adjunction property that says maps from an object to the underlying set of a monoid here. So if I picked a set here and a monoid M here, and I said we can either push that set over here and consider maps from the image to M, or I can pull the monoid back here using the underlying map and consider maps from the set to the underlying map of the monoid. That's this thing. And they're a one-to-one correspondence. So that's an example of an adjunction. Okay, so another example of a free structure, which gives an example of an adjunction, is the notion of a free category. So similarly, here we have a category of directed graphs. So we might, things like we think of, it's just some directed graph presenting. And we also have a category C. And so we can think of this thing as presenting the path category, which I normally just draw that and say, think of that as a category. But you might think about it as a functor that takes a directed graph to a category. And this sort of maps from the free category, the path category, to C. Or every category can be considered as a directed graph where the the vertices of the graph are the objects of C, and the arrows are just the morphisms, and we just forget about the composition property. So that means that there's a map from the category of categories to graphs that takes, again, this notion of an underlying graph. And so there's free construction, but there's also this map sort of called path or free that takes a graph and returns the path category. And so these two things are also an adjunction. Maps from the path category to C are the same as graph homomorphisms from some graph to the underlying category, underlying directed graph of C. So the notion of a free structure is good because it provides you a way of giving some simpler data type like a directed graph and getting for free a more complex data type like a category. And this becomes very important in applied category theory because we really want not just to sort of know abstract structures exist, but to find ways to generate them, to find out ways to sort of simply, in concrete terms, specify the category without maybe having to sort of construct all this extra information like constructing the composition rule and checking that it's associative and unital every step of the way. So in this talk, or in this lecture, we're going to talk about how these notions of signal flow graph present notions of linear algebra. So in particular, I want to talk about how a particular variant of signal flow graphs presents the proper matrices that we saw last time. Okay, so let's think about some props now. So David said that one way to think about props is that they're symmetric monodal categories where we make one of the structures, this time the objects, that really simple, instead of, say, symmetric monodal preorders, which make the morphisms very simple. So by simple, we really mean this sort of notion of freeness here. So a prop, just to remind you, is a strict symmetric monodal category where the monoid of objects is, it's one thing I could write here is free on one generator, and then there's a generalization, a more general notion of a colored prop where it's free on a set of colors, or a type prop, or free on a set of types. But I'm just going to write the natural numbers here. So what does strict symmetric monodal category mean? This is a term we've mentioned in passing, but I don't think I've written out the definition before. So strict is means that these structure maps, so we remember that a symmetric monodal category had these things called uniters and associators that helped witness the unitality and associativity of the tensor product. So strict means that the uniters and the associators, sorry, they're small, are identities. So we can kind of forget about them. In other words, i.e., before we said that x tensor y tensor z should be isomorphic to x tensor y tensor z, but now we're saying they're equal. So in particular, this means the objects form a proper monoid and not just some sort of lax notion of monoid where we witness these things by isomorphisms. And in particular, a prop requires that monoid to be the natural numbers, so to be free. Also want to cover, so here the notion of freeness sort of dependent on the notion of morphism. So let me tell you what a prop functor is. So let's say from a prop C to D is just a functor. So C and D are props, but props are categories, so we can talk about functors between them such that, and they just have this extra property that makes them continue to be simple on objects. So such that they, it is identity on objects.
You want a symmetric monodal functor?
Oh, yes, sorry. Symmetric monodal functor. So not only is it preserving well, not only is it preserving composition like a functor should, but it also preserves the tensor product. Right? So a prop functor is a symmetric monodal functor such that it is identity on objects. So in particular, both props, any prop has, again, n as its set of objects, and so we can ask that the functor on objects just be the identity. It sends 1 to 1 and 2 to 2 and so on. Okay, so so another definition we should recall is recall that a prop signature, which we talked about briefly last week, is a set of sort of things. Let's call them G, set G, with two functions to the natural numbers. So, I'll call them source and target. i.e., example, you might have, and we'll draw things like we'll say that we have some morphism A from 1 to 1, and sort of B from 2 to 1, and so on. So here, this thing is the S of A, and this thing is T of A.
Question?
Question? Yeah.
I have a question about the definition of prop functor. Is that imposing anything more on the definition of functor, or is it just a functor that?
So functors don't have to be on identity on objects in general.
But that's not forced by the fact that you're dealing with?
No, that's not forced.
Okay.
1 could go to 2, and then
Yeah.
2 would go to 4.
Yeah, exactly. If 1 goes to 2, then 2 has to go to 4. That is forced by the symmetric nodal nature, or the nodal nature of this functor, but you were still free to send 1 to something else. And in fact, because of the freeness property, in fact, where you send 1 determines where you have to send everything else from symmetric nodal functor. So I won't sort of write out the category of prop signatures, but there's a theorem that says the free prop on a signature sigma is the prop of Plot graphs. Sigma we called. Which we talked about last time. So, for example, if I take the signature, which I'm just going to draw like this, so there's an element A from 1 to 1, then a morphism, so the objects of the free prop on A, of free prop on this always have to be the natural numbers, but the morphisms are these sort of graphs we can construct by connecting these things together in series, in parallel. We can swap things around. We can have identity graphs. But that's just what a morphism in that prop looks like. So this is an example of morphism. So similarly, I don't know, another example is not very different. I'm going to call this M. If we have a map from 2 to 1, maybe I should call that V. Let's put V over here. Here's a signature. It's a very simple signature again. A morphism. And this again looks like a bunch of things.
Your B is missing
And B is missing
an input.
an input. There we are. So a sort of quick question, so you can catch your breath, is what is a prop functor? So if I call this V, what is a prop functor from the sort of free prop? Let's call it free prop on V to the nodal category sometimes. Oh no, that's not a prop. Finite sets. So I should have told you about the prop of finite sets. Its objects are the natural numbers, but you kind of consider that you consider the natural numbers as finite sets, right? N is an n-element set. And then you can talk about the morphisms in the proper finite sets are just functions between them. And sorry, that should be plus and 0 then. So there's a prop where the objects are finite sets, and the morphisms are functions, and then the monodal product is given by disjoint union of sets or addition.
So you want us to give you one, or you want us to kind of unpack what?
So yeah, so maybe find a neighbor and talk about just trying to unpack this what a prop functor should be given this result.
Formal phonetic code is a problem for the dimensional. so we have the objects. That's a six.
Sorry, it's not general.
Two ways I can think about this. One is thinking about what the props like all four with just the other thing, but the kind of more cool thinking about this is this kind of a junction where if the free prop on B is and a function out of it is really well enough by going over that's helpful to say, but what I want to get a prop function from free prop on B to fin set generating objects. And what and what B should be. Well, there are if you pick a number, all those like for your string.
You can go from like, like 3 to 2 for example, right? You can go.
Right now, any chord graph would be that one too. No, B goes from a function. B goes to a function from the set cell itself.
Yeah,
so if I take the set that's real, then that's the set plus 5 layers. So a set plus itself, I really need my twice as many elements. Once we decide where the string is, we decide how many elements we have. And B is going to be here, we're sending the same
use a B, then that's no longer. Yeah, you're right.
Let's try and bring this back in. So, does anyone, have people started to process this definition? Does anyone, can anyone tell me, for example, well, how you should think about a prop function in light of this definition? Okay, so this theorem says that the free prop on a signature is this prop, but in particular, the free prop, then a functor out of the free prop, maybe it should be the other characterization over there, is really just a choice, is a map that says, here's sort of the generating morphism of the free prop, and what morphism in the proper finite set should it go to? Yeah.
So I think it's just going to be like any set function from like one set to a set that's either the same size or smaller.
Close. So we've got to send this to a function, but this has got to be a function from some object to another, and this functor is already determinate objects because prop functors have to be the identity objects. So this is a morphism from the object 2 to 1 in the free prop. So it's got to go to a function from the 2-element set to a 1-element set.
But it seems like you get any function from m to n as long as n is smaller, or is that not?
Oh, so what is, yes, so morphisms in general, the free prop, yeah, so you're describing the image, exactly.
But isn't it a morphism from the even sets of even cardinality to sets of half that size? Because
no.
That's what I thought too. What you got was, that's what I got also.
No,
because I was wrong.
Yeah,
and that is that I thought it was a
These are
symmetric
product.
nodal functor as opposed to a prop functor.
Right, it's a prop
So he would be right if he'd written symmetric nodal functor. You'd have to pick a set for the string to go to.
Right.
And then you'd, yeah, so I got the same answer and we're wrong.
But the correct answer, yeah, is basically what you're saying. So morphisms in the free prop look like this, where each of these represents sort of the unique each of these b's represents the unique function from 2 to 1. So here I can think of this as a function from a 2, 4, 6 element set to a 3 element set. And what is that function? It sends the first element to this thing, the second element to this thing, and so on. Right? And so every surjection can in fact be given by a B-labeled point graph. And so this free prop is kind of, it's the image in here is the surjections between finite sets. Yeah.
So the definition of a prop functor says that it's a symmetric monoidal functor. Is it possible to have a functor between two symmetric monoidal categories that's not symmetric monoidal? Or what does it mean for the functor to be? Like, is that a property rather than structure?
It's an additional property on the functor. So if you're really interested in your objects as symmetric monodal categories, so somehow the symmetric monodal structure is key to what's going on, then an expression of it being key is that you should only really consider symmetric monodal functors between them. But for example, the category of finite sets has two symmetric monodal structures, and so you may not be working with respect to, you may not be working with respect to both of them. You're probably not. You may not even be working with respect to one of them. So something might be a symmetric monodal category, or have it be sort of, you might be able to equip it with the structure of a symmetric monodal category, or think of it as a symmetric monodal category, but you might not be doing that in your particular situation, and then you would just consider a plane well, that case. In that case. Does that make sense?
Yeah, I'll ask him.
Yeah. Basically, there's sort of, when you consider something as a certain structured object, you should almost always consider the morphism, the notion of morphism that preserves that structure. Okay, okay. So hopefully we have some idea of what prop functors are. Now, I want to talk about single photographs. So consider this signature. So I'm going to call it sigma, and it's going to have a morphism from 1 to 2. In fact, I won't write the types, but this is a morphism from 1 to 2 because it's a picture of something that has one input and two outputs. Have a morphism from 1 to 0, a morphism from 2 to 1, and a morphism from 0 to 1. And then I want a morphism from 1 to 1 called A for every real number A. Okay, so what is a free prop? What is a morphism in the free prop on sigma? Morphism in free prop sigma looks like this. Add things, scale things, throw things out. Maybe I can hit this thing again. Maybe. So it's.
What are those symbols again?
So these are 5 and 6. But it's basically taking these symbols and then drawing some graphs of them, and some plot graphs of them. So there's this prop functor. Which I'm going to call S from this free prop and this to matrices in the real numbers. So I'm going to call these things signal flow graphs, and you can sort of see the resemblance to that signal flow graph David drew on the board last week. It has a bunch of ways to sort of split symbols and add signals, and also ways to amplify them using these real numbers. It's a bit more simple because we're not sort of considering time-varying things and integrating and so on, but the basic structure is the same. Okay, so you can define a functor from signal flow graphs to matrices just because it's the free prop by saying where these generators go. So I'm going to send this to the matrix. Let me see what dimension I've chosen. This is the better one. So it's better because
Can you redraw that?
Sorry?
Redraw the last one. No, it's the wrong way. It's, oh.
Oh, no, okay, yeah. Okay. This is a better convention because it allows me to, so this is probably the transpose of the usual convention for matrices that you might be used to, where the rows are sort of inputs. So there's one row because there's one input. The columns are the outputs. Okay, but so saying again for free structure, saying where these generators go says where every morphism in it, so where every signal flow graph will go. So I've told you where these individual matrices go, and now if I draw a signal flow graph, I can tell you what matrix that corresponds to. Question?
How does the zero morphism works? You take nothing in, but you give something out?
So this is just purely syntactic. Right? There's this zero thing, it's this one. So there's a map from 1 to 0.
I think you want 0 to 1.
That's okay. The 0 to 1 is kind of weird.
Right. So to generate a prop, you just have to specify some symbols and some types. Right? So I'm saying that this is a symbol which has 0 inputs and 1 output. I don't give it any sort of semantic interpretation yet. But given these symbols, you can construct a prop, which is just some free syntactic thing, doesn't really have any meaning, where your morphisms look like this. This is a morphism from 2 to 2. We'll continue and maybe it'll become clearer, and if not, let's talk afterwards. Okay, so for example, let me be more precise about a morphism that I'm going to draw. I might draw a morphism that looks like this. Right. So because these things define a functor to matrices, this is a morphism in the free prop, so it corresponds to a matrix.
Would you mind adding a open circle, or would it kill your?
Like
put one there and.
Sure, I can do that. Okay, like that. Okay, so what should this be? One way to do this is by figuring out part by part by sort of this way we thought about reading diagrams earlier. Actually, I think we can do that. Okay, so this is the composite of, if we map this functorial, it's the composite of the matrix corresponding to this, which is so this thing maps to 1, 1, composed with 5 tensor. So what's this thing? This thing maps to the identity matrix on one element. So it just maps to this matrix here. And this thing here just maps to the matrix 5. But David said that the direct sum of, or the monodal product in matrices is just this diagonal product. Okay. Here, the swap also, because it's a symmetric monodal functor, has to be mapped to the symmetry in the category of matrices. So the symmetry in the category of matrices looks like this, and now David's made me tensor that with an empty matrix, but the empty matrix still has a dimension. It has the dimension, I guess it's 0 by 1, so I should add a column. So then this thing becomes 0, this, oh no, the other way around. So 0 element was on top. So it gives me that matrix. And so the image of this signal flow diagram under this functor is the composite of these matrices, which I'm going to say is 0, 0, 1, 5, 0, 0. And you can check that by matrix multiplication.
Shouldn't it be 1?
Oh, I'm wrong. No, I'm sorry. You're all right. 0, 1, 5. Yeah. Thank you. Okay, so I kind of ran past that construction there.
Yeah.
Let's see. The reason, so matrix multiplication is not normally, when we're talking about matrices, we usually do not talk about 0 by n or n by 0 matrices. But then the notion of so matrix multiplication gives you this formula that if you want the ijth entry of some composite matrix, it's equal to the sum over m I dummy variable k times n kj. Sum over k. Right. So this is some intermediate variable. But if we have a 0-dimensional element here, then this k is going to be summing. This sum is going to try and draw k's from an empty set. And so we're going to be looking at an empty sum, and the sum of nothing is by convention 0. You may also not have seen that before, but that's a very robust convention. So in particular, this thing, the 0 by 1 matrix, when we tense it with this, add an extra column and no rows, and those rows were just 0 columns. Sorry, these columns were just 0. This column was just a 0 column. Okay. To give you a better, just a couple more examples, this thing maps to AB, and say this thing also maps to a 1 by 1 matrix. Maybe I'll just get you to tell me what this one is. So here's a question. What does this one map to? And maybe also, let's say 7. Okay, so here's some questions. Tell me what these 3 signal flow graphs. Tell me which matrices that these 3 signal flow graphs are mapped to under this functor S. Give you maybe 3 minutes to think about that.
The same way how there's like 5 1 is like 8.
A times B? A times B? Or the set? Oh, well, it has to be a 1 by 1.
The 1 to 2 more.
Yeah.
And then 2 to 1. And then we're bringing them together again.
Yeah.
Those 1.
I mean, if you just write now, this is what you get. First one.
A plus.
Oh, sorry.
Oh, I see.
Great guess.
The next one.
7 times.
7 times what?
7 7.
Do you think it's a diagonal matrix?
No, it doesn't. We know that's our.
It's a 2 by 2, right?
No, 7 is it's 1 by 1 by 2.
That one? So 1 by 2. It should be 2. So it's always going to be number of this number of rows, this number of columns.
Oh, so it's 2 by 2.
Yeah. Diagonal. Oh wait, are you asking? Is that one big thing or 2 different ones?
2 different ones.
Oh,
Sorry. The questions aren't too different in that if you can answer one, you can almost certainly answer the other as long as you understand the nodal product. Okay, what are people getting from here?
A plus B.
It's A plus B, right? So it's a 1 by 1 matrix. It's got 1 input and 1 output, and the entry is A plus B. How about this one? Okay, so what's the shape of the matrix?
2 by 2.
2 by 2. And okay, I guess the answer is it's 7s, but it's all 7s. So that can be computed out. Okay, I'll give you a shortcut to think of these in a second. Anyone want to tell me what the answer here is? This one requires a lot of computation if you do it this way because there's a lot of pieces. So if you'll notice here, the shorthand for interpreting all these things is to think about what you do when you go from 1 input to 1 output. So this entry here can be thought of as the amplification over all paths. So you sum over the product of all paths. Sorry, you go across all paths and multiply all the amplifications that you run through, and then you sum over that over all paths from the ith input to the jth output. So in particular, this is from 1 to 1. So you can't get from here to here. So there's 0 amplification. For this thing, if you're getting from here to here, the only way to do it is to go through this path, and it has amplification, no amplification. So it's just 1, and the other you cross via a 5. So it's 5. Similarly here, you go through 2 amplifications, you get A times B. Here you have 2 different paths. This path gives you A, and this path gives you B. So the result is A plus B. And similarly here, you get all 7s because there's only a unique path from any 2 things, and you always run through the 7. So here, from the first input to the first output, there's only 1 path, and you get 1. From the first input to the second output, you get 4, and then you get a 2 and a 7. So there's sort of this trick to understanding, or there's this sort of signal flow interpretation to these graphs that exactly captures this matrix multiplication. So this is a non-trivial result, but this is sort of a description of this free functor, or of this functor given by out of this free category where you say the generators go to these matrices.
Question?
Yep.
Aren't the columns outputs?
The columns are outputs. Yeah. So this represents the first output, and this column represents the second output. And then I think it should be first input to second output. So first row to second column. Sorry.
Yeah, it's transposed, I guess.
I transposed it. Thanks. Okay. So there are some questions you can ask now that we have a way of sort of drawing pictures and having them represent matrices. One is that, does every matrix have a picture? Right. So the answer to this is given, I'll give you a bit of category theory terminology. A functor from C to D, let's call it F again, is full if so for all xy, C of xy, so a functor gives us map from C of xy to D of f of x, f of y, is a surjection. And so in particular, using this bit of jargon, you can answer the question, does every signal flow diagram have a matrix with, sorry, every matrix have a signal flow diagram with the theorem that S is full. So for every, it's always a surjection of Hom sets. The Hom sets are the matrices. So there's always something down here that maps onto that. There's always a signal flow diagram that represents any matrix you choose. And so the proof sketch of this, let me just do it here. The idea is somewhat like this. You can see that if you swap out these numbers, you can generate any 2x2 matrix. And in general, because you're doing this path counting thing, if you want sort of a 4x3 matrix, what you do is you sort of, for every input, you duplicate it as many times as you have outputs. Then you, so we do that here too. Then for every output, you sort of add one single thing for each input. And then you connect up, so then you have sort of a bijection between these things and these things. You connect up sort of the first one from the first input to the first output, but given by amplifying by the entry of the matrix that you want. So this is, if you want the matrix sort of, that begins with 2 in the top left-hand corner, you put a 2 amplification there. And you can construct a signal flow graph that represents your matrix in that way. The second question then is that now that you know you can represent every matrix by a signal flow graph is how do you figure out when two things are the same? For example, if I ask you to represent, let's see, this matrix, you might give me this thing, but you also might give me this.
That's the same, right?
Okay, you also might give me that. You also might give me this. Right? And it turns out that, I mean, doing the path counting thing or just computing out the matrices, you can see that this thing, these two signal flow graphs correspond to this matrix. So it turns out that you can axiomatize, give a representation that describes when any two matrices when every two signal flow graphs represent the same matrix, and the answer is given here with this set of, I think it's 17 axioms. Yeah. Here's something I prepared earlier, I guess. So what's going on here? It looks like a lot of information, but really it boils down to a bunch of simple axioms. So, for example, we saw this notion of a monoid earlier in an arbitrary monodal category, and a monoid has a multiplication, so a thing that takes two things and returns one thing, and it has a unit, which is just an element of one thing. And so these axioms here capture this notion of a monoid by saying, if we multiply things and multiply them again, if we have three things, we multiply the first two, then multiply that with the third one. It's the same as multiplying the second two and multiplying that with the first one. So that's just a picture of associativity. And this happens to be a picture of unitality, and this is a picture of commutativity. Similarly, these things are the same, but transposed. These are pictures of the notion of a homomorphism, and these are the pictures, this is a way of that. So we call this a comonoid, and there's this sort of well-known way that comonoids and monoids can interact, called a bimonoid, that you see a lot of representation theory through the notion of the bialgebra. And so this is just saying that that happens. But the point is that this gives us a sound and complete axiomatization of matrix multiplication. So given any question you have about matrices, if you want to represent them in terms of signal flow graphs, so with matrices, you have this way of reducing matrices or computing with matrices called matrix multiplication. And that tells you when two matrices or two composites of matrices are equivalent. Here, this plays the analogous role. These 17 rules allow you, if you're working in the world of signal flow graphs instead, to determine whether two signal flow graphs have the same meaning, represent the same matrix, or represent the same structure in your application. Okay. So, we've got 5 minutes left. matrices get you some of the way towards linear algebra, but if we only permit ourselves these sort of operations that were allowed in the world of props, we can't actually talk about all of linear algebra. It's very difficult to talk about kernels and images and eigenvectors and things like that. But you can get closer in quite an elegant way through the notion of a linear relation. So, and then this has a really nice graphical linear algebra, graphical perspective. So the main trick here is that, and this sort of, you can see in this work on signal flow graphs, so you can see it's sort of been long noticed by engineers, is that the orientation on the plane is kind of irrelevant for the semantics. If you have one of these symbols, if it's an electrical component or something, you can always turn it around. It doesn't have this preferred orientation that these things have that say everything goes like this. This symbol always goes from 2 to 1. Okay. So you can ask questions like, we know that this thing represents the matrix 1, 1, which sort of we think of as adding two signals. But what should this symbol mean? Okay. Intuitively, it should sort of mean that we add signals coming in from that direction. But that's no longer a function, because if we're trying to interpret these things as matrices going from left to right, then there is no matrix that kind of adds things from the other direction. But we can return to this notion of a binary relation, which we talked about in the first lecture. Right, so this thing, it might represent the matrix, but this thing has sort of this equivalent data to saying, it says that if we take a x, y, z tuple, which we think of as lying in r times r for the beginning, so r squared times r, then we enforce the constraint that x plus y equals z. And now this is a much more symmetric structure, and we can flip this around. So instead of interpreting these symbols as matrices, there's this prop known as the prop of linear relations, which is where the morphisms, so in rel as a prop, so we need to talk about the morphism from M to N. The Hom set is the subspaces, the linear subspaces of R to the M direct sum R to the N. And you can compose these like you compose relations. So flipping this around, we have that this thing now interprets, not in matrices, but in linear relations, as this sort of set of x, y, z tuples, such that x equals y plus z. And this is seen as a morphism from r to r squared. So and now, for example, then, if we have a big matrix, how do we think about something like the kernel of this matrix? Well, we want to find all vectors that map to 0. And how do we represent the zero subspace? Well, this thing already, as we sort of talked about earlier, represents the element 0 lying inside sort of the zero-dimensional vector space times R. So if we flip this around and put zeros here, this thing represents a subspace of just the vector space generated by these inputs here. And in fact, this is the kernel of N. So for those of you who have seen this notion in linear algebra, that's kind of fundamental to analyzing matrices. And you can kind of carry out the story in more detail. So I think I'll end there, but just to summarize, there's this sort of world of signal flow graphs which roughly takes place over, instead of this field R, you can enrich it with sort of greater structures that can talk about integration and sort of differential equations a bit more, but keeping in mind the linearity of the underlying situation. And then, so you can draw these graphs. These get formalized through this notion of a prop. And this sort of notion of a prop helps you sort of reason about linear algebra. It provides this sort of overarching algebraic structure where all matrices live. Thanks very much.